Hello students, welcome back. In the previous lesson, that is in lesson 4, we studied the initial value problems associated to linear ODEs with constant coefficients. Here is lesson 5, let's focus upon the general solution. Here's a motivating example. Extremely simple equation, but no initial condition. How do we handle it? The first step is to create the initial condition artificially. Let's name y of 0 as y sub 0 and y prime of 0 as y sub 1. Okay, now that we have at least tentative initial conditions already, let's go with the Laplace transform. Take the Laplace transform of both sides, and please take a look at the right-hand side. That's 0, so right-hand side is always 0. Now, how about the left-hand side? By the input derivative rules, the derivative y prime becomes this, and second derivative y double prime becomes that. And then, let's take the like terms together. The coefficient of y term put together, we get this part, and the other, we get this. And then flip the other part over to the right-hand side and then divide by this coefficient part. What do you get? We get this fraction expression. We get a rational function. Now pay attention to the degrees here. The numerator has degree 1 at most. Denominator has degree 2. So this is a proper rational function. So we can decompose a partial fraction using the usual theory. Now, if you have some polynomial part, the quotient part, things can get messier. This is already messy. I mean, all partial fractions are messy, but at least this follows the standard theory. So what do you get? Oh, not this one, the next cell. Yes, this is what we get if we decompose a partial fraction. Factor the denominator, and then we get this form. And then what do we have? We have the first function and the second function. And then taking the Laplace inversion, we get the first solution and the second solution. These constants C1 and C2 will be determined later from the initial conditions. Now, if you have some other kind of initial condition, like y of t0 is something, and y prime of t1 is something else, something. If you have something like this, then you're going to get two unknowns, C1 and C2, and you're going to get two equations from here and there. So you have a system of linear equations to solve. Tedious, but you can do it. This way, you can handle any kind of initial conditions here. These do not have to be zeros. In the previous lesson, in lesson 4, we had to have y of 0 and y prime of 0, y double prime of 0, and so on, because we need those for the input derivative rules here and there. But by considering these in a little bit more general form and getting the general solution, now we can use any kind of initial condition. That's where we are headed. Of course, this was just a simple exercise, very simple motivational problem. So here's the plan. After this, we're going to take care of some terminologies, and then we're going to go over to the theory of the Laplace transform. And then we're going to go to some real examples. That's the plan. Ready? Okay, let's begin. Let's take care of some terminologies. Homogeneous versus non-homogeneous linear ODEs. When the right-hand side is 0, we call it homogeneous. If it is non-zero, some other function, then we call it non-homogeneous. Now, some students get confused with the homogeneous equations that we studied in lesson 3a. The homogeneous equations of first order that can be transformed into a separable equation through appropriate substitution. That homogeneous equation and this homogeneous equation are a little bit different. As a matter of fact, deep down they are related, but I don't want to go there. So at this moment, just consider them as separate entities, even though we use the same term, homogeneous. So homogeneous equal to 0, non-homogeneous equal to some non-zero. Next term, characteristic polynomials. This time, let's consider a linear ODE of order n with constant coefficients. This time, coefficients are constant. Previously, we didn't have to have constant coefficients here, a0 of t, a1 of t, and so on. Now we need constant coefficients, a0, a1, a2, and so on. It can be either homogeneous or non-homogeneous, it doesn't matter. Either way, we can define so-called the characteristic equation of the given ODE by taking all these coefficients and forming an algebraic polynomial, an s to the nth power, an minus 1, sn to the n minus first power, and so on. Set it equal to 0, then we'll call it characteristic equation. The zeros of characteristic polynomial, or equivalently, the roots of the characteristic equations are going to be called the characteristic values or eigenvalues. And yes, these actually correspond to the eigenvalues we study in linear algebra. If you didn't take linear algebra, never mind. In any case, I'm not going to go too deeply into that anyway, because getting the connection is going to be a big deal, so not here. Maybe in differential equation 2, I may consider it, but I'm not going to consider it at this moment. Not here, not right now. So I'll try not to use these terms, characteristic values or eigenvalues. But as for characteristic polynomials or characteristic equations, those are necessary, and you should know those. How do you get the characteristic polynomial? From the coefficient of the ODE. Okay, so much for the terminologies, and let's begin. Let's begin the theory of Laplace transform, homogeneous case. Let's begin with a homogeneous linear equation with constant coefficients, like this. And then, as before, let us create the initial condition artificially. Now let's take the Laplace transform of the both sides. And then the right-hand side is 0. And then y becomes y, and then y prime becomes this by input derivative rule, like this. And then y double prime, and so on and so forth. And then nth derivative becomes like this by, again, the input derivative rule. Let me show you a little bit more so that you can see the pattern a little bit better. So here, that's the nth derivative. And then this is the first derivative. And then this one, some other color. Some other color. Okay, all right. Just to help you see the pattern a little bit better. Okay, now take the like terms together. If you take the like terms together, you're going to get something like this. You will get the characteristic polynomial. Why? Let's look at the y term here. We get s to the nth power times y, which I'm highlighting in bold. And then s to the n minus first power times y, and so on and so forth. S squared times y, s to the first power times y, and this one I'll put in s to the 0 power in. Now, pay attention to the bold part. Y will be factored out, of course. And how about the coefficient? an s to the nth part, red. an minus 1 s to the n minus first power, pink. And so on and so forth. And then a1 s to the first power, green, and then the final one is black. You see, we get s to the whatever power times the coefficient. Those are all coming from this input derivative rules. So conclusion, we have to have the characteristic polynomial here. Actually, that's a full proof. And then how about the rest? How about the rest? Well, the biggest power I can get is n minus second power. No, n minus first power, excuse me. That's the biggest as you can get. Next one will be n minus second power and so on. So biggest will be n minus first power. If y0 happens to be 0, then not even that. It'll have to go down even further. So this part has to be, at best, at the highest n minus first power, or less. So flip this to the other side and divide by this characteristic polynomial here, then we're going to get r of s over q of s. And then, as I told you before, this one has power, the degree of n minus 1. As a matter of fact, this is not entirely correct. It should be less than or equal to. You see, if this coefficient happens to be 0, then it may have to go down further. If this y of 0 happens to be 0, then it may have to go down further. So it's less than or equal. In any case, the degree of the numerator is less than, strictly less than the degree of denominator. That much is certain. So this rational function is proper. By the way, does everybody recall those rational functions and something you did a long time ago in college algebra days? If you have a rational function, it can be written as quotient plus remainder, kind of like this, or equivalently speaking, division algorithm. This is quotient times the divisor times and plus the remainder. Do you recall this kind of thing? This one is called quotient. That's remainder. And I'm using r for remainder here. There's no quotient here. Quotient is always 0 because the denominator has higher degree. Quotient is always 0. I cannot emphasize that too much. Okay, this is proper. Therefore, once you take the partial fraction, the usual decomposition rule applies here. If you have quotient, then we have the polynomial part there as well, so it'll become even messier, but luckily we don't have that. So upon taking the Laplace inversion, you're going to get the general solution. So that's the theory. As for the partial fraction, it's always messy. So instead of showing you the general form, which I will actually do in a couple of weeks, using the fundamental theorem of algebra and whatnot, but at this moment, let's just go with an example to show you the general theory of the partial fraction, how it is going. Let's begin with, oh my goodness, this linear ODE with constant coefficients. Okay, all right. Look at all these numbers here, and this is something this is clearly not the kind of thing you can handle with just paper and pencil computation. Of course, you're going to need some technology help. So, what is a characteristic polynomial? Well, there you go. That's a characteristic polynomial. And then it can be factored like this. And of course, I don't want you to do this with paper and pencil method. This is the way to go. Factor, and then I'll ask Mathematica to do that. I got this. As a matter of fact, I got this problem from Mathematica to begin with. Expand and then that thing. Oops, wrong key. And that's how I got the original problem to begin with, as a matter of fact. Expand command, factor command, they're both useful. Okay, factor, and I got it. And then some further manipulation. Take all the coefficients out and then make each factor monic. So all the leading coefficients here, here, and there are 1 from now on. Now we are ready. Take the decomposition by partial fraction. This one goes up to first power, so I have C1 over denominator, no problem there. And this one goes to the third power, so I need 3 of them. First power, second power, third power. Have you seen this before? In Calc 2 we do this, but of course not with really complicated problems. But we do study the general theory there. Now for quadratic irreducibles, so this goes to second power, so I have 1 and second power. But the numerator should be linear. Because denominator is quadratic, the numerator should be linear. Alright, we have green, red, and blue. And then let's take Laplace inversion. Green becomes that, and I hope you guys remember the table. This is 1 over s minus a form, so it's exponential. And this one, 1 over s minus a form, so it's another exponential. This one is squared, so we need t times that. This one is cubed, so we need t squared times that, and so on. How about the blue part? Those are sines and cosine. So this one has first power, so we have exponential times sine. Exponential comes from this translation. And that this is squared, so we have to multiply another t. So, yeah. Exponential cosine times t, exponential sine times t. We are done with the Laplace conversion, Laplace inversion, excuse me, and we got the general solution here. K1 through K8, and those constants should be determined by appropriately initial condition. By the way, and one more comment here. As you saw, the general solution can be written as a linear combination of these Laplace inversions given by the decomposition by partial fraction. And these functions are called standard basis functions. That's a term our textbook author is using. Names are not that important, but I'm going to be using the standard basis function from time to time, so maybe it's a good idea to get used to it. Our textbook author uses this script BQ to represent the standard basis function. Obviously B for basis and Q for this characteristic. And as for actually getting this decomposition by partial fraction, don't worry too much about it, and you're going to be using computer anyway. We have some time left, so let's go ahead with the same example in complex numbers. And you can completely bring those down into complex roots, unlike the previous case. And the blue part end up with e to the at, where a is complex. So e to the a plus bi t, that kind of form. And these constants here, coefficients, C5 to C8, those are complex numbers. But that's okay. And if you put in those initial conditions and then do the computations right in the end, then you're going to get everything down to the real numbers anyway. And the reason I like complex numbers is because there's a nice thing called the fundamental theorem of algebra that certifies this kind of factorization is always possible and always complete. Therefore, if you go over the complex numbers, solutions are always there and always unique and everything. And that's why I like complex numbers. And also, if you go a little bit higher up, most of the time you have to deal with complex numbers anyway. And Mathematica is also built up on complex number system. Our textbook is built up on real number systems, so we're not going to go too deeply into this, but in any case, we did it. Okay, so much for the theory, and in the next video, we'll do some examples. Lots of examples.